Alright, so I had my memory card fill up on me again, so I've already got a little bit started here, but I'll start from the beginning. This is what we know in the supplemental problem for 31. Resistance 10 ohms, magnetic field 0.1 Tesla, and the time interval is 0.1 seconds. We have this square, which I drew really small, unfortunately, and if the sides are all 3 meters, the area is obviously 9 meters. And this line right here is 3 times root 2. So if we take these points here and we pull them out so that this becomes 3, that goes down, it lowers, and that makes it a parallelogram where this side, and this side are all 3, so the angles are all 60. They are equilateral triangles on both sides. And then we get the area for that, which I'll call area 2. And I guess we kind of have to get that value right there, that height. And I did it by some weird roundabout way that isn't really even worth talking about, but I guess I know I probably could have just used a right triangle, but I like to throw in this law of sines every now and then just so that I don't feel like I wasted my time learning it. So that equals sine of 60 over sine of 30. And the actual height comes out to be 2.598. So then I guess if these are equilateral triangles, we can just find the area of one of them, multiply it by 2. So that area 2, I will do it down here. Area 2 is going to be 2 times 1/2 of the base. The base, 1/2 of that base, I guess it's just going to be 1.5. 2 times 1.5, 1/2 of the base, which is that, times the height, which we already know is this. And that will equal, just make sure that actually comes out to what I thought it was going to be. What do we got here? Now you can't see my calculator. 2 times 1.5 times 2.598. And that does come out to what I wanted it to be. See, I used some weird parallelogram geometry that was completely unnecessary the first time I did it. I should put that up here too, meters squared. So our new area is going to be 7.794. So what we're looking for is the current that's in the loop. We know the magnetic field is going into the page, perpendicular to the page. So we know that the magnetic flux is simply going to be B times A. That's what it is, because it's perpendicular to the page. So if we want to find the change in magnetic flux, since magnetic flux is BA, we can say that it is 0.1, which is magnetic flux, times the final area, 7.794 meters squared. Subtract that by 0.1 times the original area. And so we get our change in flux to be negative 0.12 Weber. I said this before the last time when I first did this video before the memory card ran out, that I'm sure there's better ways of doing this problem because these numbers keep cropping up. And when I see the same numbers coming up over and over again, I usually think there's a better way to do it. But this is how I did it. So that is our change in flux. And we know that an EMF, because of Faraday's law, is going to come up. It's going to be created because of this magnetic field. And that's going to equal negative the change in the flux over the change in time. So we know that the change in flux is that, and we know that the change in time, which is our time interval that we got right up here, 0.1 seconds, equals that. So that comes out to be, it's negative also. So it comes out to be a positive 1.2. And 1.2, coincidentally, is the difference in the area. I didn't really, it's one of those things I was talking about where something screwy in the problem. I probably could have done a lot less steps. Anyway, so that is our EMF. And if we want to find our current, then that is the absolute value of the EMF, which doesn't matter because it's positive, over the resistance, which becomes 1.2 over 10. And we get the answer to be 0.12 amps. 0.12 and 1.2 come up a lot in this, and I have a feeling it's because of the geometry. So that is the current in the loop, and let me see if I can draw out a loop here. We'll just say that's what it is. We got a magnetic field going into the page. So if it's going into the page, our fingers are going down. We're grabbing that loop anywhere we are, and it's always going this way, clockwise. And I believe that's all that was asked for, right? Average current. Yeah, that is the average current and the direction. Yep, so that's the answer.